Okay, good afternoon. This afternoon we are going to talk about wood. As you may know, you are going to be presented with the whole of materials into this course, especially trying to concentrate on what is the research on material science. And to do that, of course, we need to understand not only which are the materials, which might be also trivial, but what are the problems related to the single materials. As in many cases, also with wood, it is interesting to start with an Ashby diagram where the presence of wood is emphasized. Um, as always, the numbers are less important because the numbers can always change. The question is that wood is dependent on fibers, on their fiber lengths, which depends on the tree from which wood has been cut, has been obtained. And in case of waste, it might depend of the way waste is treated. As you may understand, more and more materials are obtained from waste instead that from new material. In fact, we are now talking about secondary raw material. What was defined and is still in common language defined as waste, it is in reality the secondary raw material. So a material which has been used for the second time, at least. In the case of wood, what we see is the fundamental Ashby diagram, which is the one with density and Young's modulus. And you can see that you have a relative stiffness in practical terms. So you have the stiffness on the y-axis and you have the density, therefore you have a relative stiffness as a whole. Every point gives you a relative stiffness of your material. You can see that there is this big dependence on fibers, and in most cases we would like to cut the wood along the fibers, to have long fibers, also to compensate for the limitation that wood has, which is tension. Wood doesn't work very well in tension. It's not as bad as concrete in tension, but it's not amazing in tension. Wood works very well in bending. That's the way we measure. We measure it because bending is the property for which wood is usually employed. So, okay, we have also a big variation of density, which is characteristic of this material in terms of density. We have around an order of magnitude. We can easily say that we have an order of magnitude. There are some kinds of wood which go as low as 0.1 in terms of density. Here you see 100, but it's 0.1 if the density of water is 1, taking the density of water is 1. And there is a big variation also in terms of Young's modulus, because if you pass of Young's modulus stiffness across the grain or with the grain for balsa wood, which is one of the lightest one we have, we go to we can go from 0.1, which is very low, to a few gigapascal. Let's consider that we are much lower than is much well, it much less rigid than it was the case for steel. Steel, it's 210 gigapascal in tension, because the force with which steel is used is tension. and here we are much lower than that. Orders of magnitude below. 1 or even 2 orders of magnitude, even more orders of magnitude less than steel. Okay, and there is a limitation which is given by the density of cellulose and of lignin, which is the maximum density of cellulose and lignin is around 1.4 1.5. So this is the technological limitation in terms of density of wood. You cannot have wood more than 1.5. In practical terms, most woods float, so they are lighter than water. But this depends on the fact that there are larger porosities, and also that some parts are softer, some other parts are harder, even in the same tree. Some parts cannot even be used as wood, like the so-called bark, and apart from the case of cork, which is the bark of a tree, but in normal cases, bark is not used because it is too hard, but in practical terms, it is not workable. As in all cases in materials technology, there is this contrast between being workable and being hard. The harder you are, the less likely you are to be penetrated, but on the other sense, you are not able to be worked. So we can we can use wood from trees, from the so-called solid wood, but this is unlikely to be the majority of wood, the largest part of wood which is used now. In general terms, what we use now are fiber boards. And fiber boards means that we have some layers of materials which are put together by glue, bonded, therefore together, or pressed together. And what happens with wood is that they are mixed with plastics. They are mixed with plastics, and in some cases with some resins which are very popular for use with wood, like melamine, which constitutes the face of chip boards. Chip boards is a board constituted by chips, so basically by little bits of wood, which are cut in some cases from waste, in other cases from new wood, but wood which hasn't a long fiber. And therefore it's preferable to make chips and to bond them together and with a resin. So depending on the density, we might have high density fiberboard, medium density fiberboard, or low density fiberboard. But apart from these details, it is important that we are starting to talk about polymers. And polymers are chain of constituted by different molecules. Usually we repeat always the same molecule, but it is not always the case. And we have basically two types of molecules, which can be thermoplastic or thermosetting. In common people word, this would be said easily by the fact that thermoplastic melt and thermosetting burn. This is a very simple way of distinguishing them, and it's true. It is like that. In a more sophisticated way, we can say that they soften when heated, thermoplastic. They don't really melt, they soften, because crystals melt, whilst amorphous structures amorphous solid soften. This is not just a sophistication, but it corresponds to a reality because, as you have seen in the previous lecture, talking about rheology, so the way that materials flow, so the way that materials are able to fill a mold and to be molded and to be cast. When materials soften, they are not really liquid. They are sort of a fluid which needs some pain to be processed because they are not even a Newtonian fluid. So they are not fluids like may have oil, for example, which fill the bottle, whatever its size. And instead you might have some problem into this kind of molding because it needs some mechanical action, some force, or some particular velocity, or some particular arrangement of the material in order to fill the mold and so to be produced. When we are going to talk about injection molding, one of the last lectures, we are going to see that this is a very, very diffuse way of producing plastics in injection molding. So basically, you inject plastic in the mold. You have a number of limitations in doing that, but the advantage is that you can produce millions of pieces like that. However, not all materials are moldable, can be processed at a softening state like thermoplastic, because thermosetting instead have the advantage to be processed at room temperature, which is good in some places, in some open air, for example. If you work on the construction industry or if you work on shipbuilding, you are unlikely to have a mold at high temperature. So you do everything in open air and almost everything at room temperature. And this has a disadvantage, however, when you get at end of life, because in reality you are not able to remold, to recycle. You can recycle wood, you can recycle it. You can recycle by chopping it, making some small chips, making some powder, and putting that powder, that wood floor, as we call it, somewhere else. But you cannot soften it. You cannot remold into another material. You cannot have the thermal recycling. This is a limitation, and it's becoming a big limitation. On the other side, we need thermosetting resins as we need thermoplastic ones, because thermosetting resins are exactly processed at room temperatures, and we are much more flexible about the size and the geometry of the structure we can make. In practical terms, you can injection mold some materials, thermoplastic materials, but it's unlikely to fill a mold which is a few meters long. Here, in that case, you find problems because the material is not conductive, because the material is, and therefore it's heated, and it cools down in different ways with considerable temperature difference from one side to the other. In more practical terms, when you do a cake, when you bake a cake, you could bake a cake of a very large one, and there are even ovens which are very large, and you could bake a cake of meters of diameter. The real question is then ensuring an even temperature, so an even cooking of your uniform cooking. because it is not conductive, because flow and whatever comes from sugars, cellulose, etc., is not conductive. This, I am not saying that because I want just because of a joke, but the question is that there are two big research teams how to make wood or better cellulose, lignocellulose structures conductive, more conductive at least. And the other question is how to make them moldable. You can do that. There are ways in which you can make a good sort of thermoplastic. And then you have a subcategory. Basically, what happens into thermosetting is that you put a hardener, and what happens with your hardener, that you have a cross-linking, and basically all these chains are linked together, and they are not able to melt, they are not able to be softened, because they are not able to unwrap from each other, to detach from each other. They are fixed in their position. And basically, when you reach a high temperature, everything is degraded and destroyed, but you don't break really the cross links. In the case of elastomers, elastomers are again polymers. We are going to talk about them also in the next few lectures. But elastomers have the characteristic that they are able to be extended by a very large amount, so they have a very high strain. They have a very high strain, and they recover more or less elastically. The first materials we had, which had these characteristics, were natural ones, natural rubber. And natural rubber obtained from caoutchouc or from other plants. There are a number of plants from which you can obtain a sort of rubber, were thermosetting. But you can also make some thermoplastic elastomers. In particular, some polyurethanes or polystyrene, but polyurethane had a very large success, for example, as filling for sulfates. From the 30s, we had this huge amount of thermoplastic polyurethane, which finds some difficulty into being recycled as well, for other reasons, not because it's not thermoplastic, but because it's formed. It's formed, it becomes a foam, and therefore it's very, when you try to melt it, to soften it, it softens, but it loses lots of properties. So, okay, wood can be considered thermoset, and basically you have what you have in wood, simplifying to the maximum. You have a lignin, which is hydrophobic, and you have cellulose, which is hydrophilic. And lignin is alcohol-based, basically, some natural alcohols, a mixture of some natural alcohols. And you have cellulose, which is a polysaccharide, so a derivative from sugar. In between, you have also hemicellulose, which is a derivative of polysaccharides, but arranged in a less structured way, so more fuzzy, if you will, and with a crystalline percent even lower than the one of cellulose. The bulk of it is amorphous. So this study on natural materials, one of the objectives of Ashby, of Professor Ashby, in the 70s was, back in the 70s, was to recover our relation with natural material. Because in reality, in the 70s, it was the boom of plastics, and we were carrying on using some natural materials. Basically, we are carrying on using wood and using rubber, natural rubber. All the rest of it was more or less gone. Natural fiber had gone. Um, there was no interest in using some waste, any waste. There was also leather, which was used, but was not very, not in a very structural way. And cork, of course, which is a niche market, which is a subset of wood, if you want. It's a kind of bark, but again, to a very limited market. All other materials were obtained from were obtained basically from synthetic processes. Um, there was this reflection which started carrying, well, this was innovative in a sense. It was in coming back to the origins of humanity, because humans, of course, started using natural materials. More than that, they started using local natural materials, so 0 kilometer natural material. I started with the example of Ulysses, which was using olive wood because there were olive trees, and so it was the obvious way to go. But with a new sensitivity to this kind of materials, it is possible to reason on the fact that, for example, some ceramics have always been used, for example, in construction, apart from wood, rubber, water. Then there was ceramics, of course, some like sand, but not really as a structural material, as a filler, more as a filler, and limestone and the production of cement, which was in need of very high temperatures, so and bricks, etc. So there was a little bit which was left, but it was important to understand whether there was a possibility to open the field to other materials, and to investigate some materials which have always been around, but we never thought of. For example, potato skin. Before these investigations by Ashby, and for what followed, nobody had thought what was the stiffness of a skin, of a potato skin. Which is not just an academic exercise. There is also another question, that they can become waste, or we can extract some polysaccharides from potato skin, or we can use them to make composite, kind of composite, because most of these materials have a kind of fibrous content. So we can think of this. I don't go into details into that because I would need just one lecture just to go around this. But the question is, they started again to investigate this kind of material. So it was obvious the influence of fibers, and it was obvious also another thing, that these materials concentrating on wood and lignocellulose materials would have very potentially very high properties if they were crystalline, which they are never. And this opened a field of research which was important, which is still important, the field of nanocellulose, of nanomaterials, nanomaterials obtained from natural materials. because you can obtain also graphene, for example, you obtain it from carbon fibers, which in principle, well, you have graphite, which is natural, you can extract it, but graphite is subject to cleavage, and so you get layers of graphite, like carbon fibers is synthetic. And you, from carbon fiber, you can make a very crystalline one with very thin layers and very well organized layers, and you have graphene. Here, we can do that. The discovery is that we can do this kind of process also with, for example, cellulose. The discovery was that cellulose, in principle, was as stiff, if you can see here, was stiffer than or stronger than aluminum, for example. But on the other side, the real cellulose, the one which we know, which is mostly amorphous, which we know in paper and in packaging, we use a lot of cellulose for packaging. Well, it's not as stiff as aluminum, is way down. So it is all a question of getting it crystalline or amorphous. But this was one thing. The other thing was the involvement of waste. When these materials started to be waste and to be considered not just burnt or dumped, then we discovered that they have a lot of potential. I myself studied, for example, the fibers obtained from banana skin, which you can imagine that it's we have bananas in every supermarket, but we never investigate what was the strengths of this kind of fibers. This is important because in the end you can take a waste which nobody cares of and make a material of these fibers. Make also some textiles, maybe, because there was also the rediscovery of natural textiles, which is another thing which is important. So lignin is made of these alcohols, and these are the so-called precursors. Precursors means that there are different blends of these alcohols, and then some complex cross-linking of these with other molecules and other benzenic rings. And basically, you get this material which gives the structure to the tree. Instead, the cellulose allow the trees to be able to absorb water. And well, that's the main role of cellulose into trees, and also they are able to also enclose some sugar solutions, and in practice, since they are polysaccharides, they tend to absorb other sugars, etc. So lignin forms the xylem, which ensures the transport of water, because you need a stiff structure to transport water from the leaves to trunk and branches and leaves. And you have instead the other function, which is performed basically in contrast. What you get from the leaves is then transported by, you have also the opposite transportation from the leaves, which act as solar panels. You have this energy which is transported and allow the growth of the tree to happen, to take place. But basically, the energy acts as a catalyzer for the reactions happening, and the cell growth and so on. So In reality, we are far from an ideal material. Remember the material which was elastic, homogeneous, and isotropic. And I have probably already said that it's like an ideal man or woman which has the only defect of not existing. Well, but it's like as a model. It's good as a model. Well, we tend to that. The materials tend to be isotropic, homogeneous, and elastic. Then we have the limitation that if it is too elastic, so it has no plastic deformation, we are not able to work it unless we remove materials like with marble, or it's very brittle, or it's very brittle. Then it's homogeneous. Homogeneous means that it's going to be very, very strong, but in another sense, very heavy because it has no voids, no pores. Then isotropic, well, it is ideal, but it has little use because in reality we always use materials according to one force or to complex forces, but anyway, not forces coming from the three directions in the same way. And wood responds to these characteristics. You can see here that also in terms of cost, the material which is better in terms of wood ones is the one that has got longer fibers. And usually the first use of wood is with longer fibers. Then you can have cheap boards coated with solid panels, with ash wood, for example, or with melamine, which gives you the idea to be wood, but it's not wood, it's a resin, which is impressed in a way to look wood. Then you can have a strand chipboard, the OSB, which are very diffuse, especially in the last few years, because OSB require less glue than chipboard, require less energy because you don't get to the final smaller chips. You stop a little bit before. The disadvantage of OSB is that it's not very nice to look at, and that's why in some cases they are covered or they are hidden behind something else. For example, you use them the bottom part of wardrobes and so on, the back part, back side of the wardrobes, and in that case it works. Then you have laminates, and we are going to have a lot of laminates into composite, into polymer-based composites, so glass fiber, so fiberglass, carbon fibers, composite, Kevlar fiber composites, and others, because the revival of natural fibers has also been into composites. So you have laminates. You have also structures which are empty, which are cellular in the inside, like the veneer face with honeycomb inside. And you can have some situation in which it's very important that fibers are aligned in some way. And so in solid wood, it's very important because, for example, one application is the one for musical instruments, for example. And in that case, you need to be sure that the speed of sound, the velocity of sound, is the one you want. Because otherwise, the bow doesn't vibrate the way you want. And if different performance and lower performance, and lower cost as well. And in these cases, you may consider that there are very large variations of price, passing from a violin that you give a beginner, which is 8 with 8, or a violin which is used by an important player. In fact, for some important players, say would use a particular kind of bows produced by a particular kind of wood, usually, for example, the Pernambuco wood, and with a defined speed of sound. Some harmonic consideration, which I don't make, but it's very important as well, because it's not just the velocity, but it's also how it vibrates, all the harmonics, the way sounds fades away. Okay, passing to something which is more physical and chemical. The temperatures at which lignin degrades, of course, is much lower than the one at which, for example, steel melts. But the fact, well, we already know that wood is basically thermoset, so we don't expect a really melting temperature, but there is a degradation temperature. In some cases with cellulose, we might have a kind of thermoplastic. Also with cellulose, also paper, you know all too well that paper doesn't melt. Paper burns, but so cellulose in principle burns, degrades at the temperature which is around the one for lignin, but it is much, as you can see from here, this is the thermogrammetric tests, which are often done. You have a differential one, so you start seeing all the curves that represents how much of the material degrades at that particular temperature. For example, you can have the rate of mass loss, say 270 degrees for hemicellulose. It might be 0.75%, for example, 207. Or you can consider the whole of it. So we start with from 100%. Then we have some water. It dries, the first thing happens, it dries up to 100 or a little bit more, because then there are some sugary solution which can dry go away at a temperature which is higher than 100 degrees. At a certain point, it goes down. You have the onset of degradation. At a certain point, it might be faster, it might be slower, but in the end, it goes down to some amount of material which is left in the end. So basically, cellulose, nothing is left from cellulose at 400 degrees. That's why there is, by the way, there is so much interest into burning paper. If it was just paper, which is not normally the case, you burn paper, you at 400 degrees, you have no ashes. Very well, no ashes would not be thermodynamically possible, but you have very little ashes. You don't want to do as the politicians that they say there are no ashes. There will be some ashes anyway, even if you burn just pure cellulose, which would be crazy on economic point of view, by the way. But apart from these considerations, in other cases, you can see that hemicellulose there you have 20% left, and lignin you have a lot left. Even at 800 degrees, probably it's not finished even at 900. Something will disappear yet, and you get, in the end, what you get, just carbon, graphite, basically. But not oriented, just carbon, really. And it might be more or less. In a considerable way. It's not just a question of small differences. You can pass from pure cellulose, which has really a few percent of carbon emissions left, and you can have which might have still a considerable amount. So what's happening in the last few years? I am saying these things because, for example, lignin has been reused into asphalt. There are a number of the two materials that basically include any sort of nasty, shown last time to you, human hair introduced into cement, which is strange in a sense, but in the other sense is something that makes sense if you have too many of these materials, and on the other sense you want to reduce the price of your cement, and with something that provides some tensile strength. With asphalt, you can put some lignin waste. In reality, the idea, for example, here it's an example, but you could do on any kind of. Why they do it with corn cob waste? You have a lot of corn cob waste. It has no use, and also the lignin is so little percent that it's probably not worthy to try reusing to, say, furniture or whatever, or wood plastic composite, so some kind of composite with wood, some other plastics. Also melamine coated wood panel would be kind of wood plastic composite. It's not worthy because it's too little in terms of percent, but you have a lot on the other sense because you can have very big fields, and so it is also interesting because you can get to the so-called circular economy, which again thermodynamically is an absolute also circular economy because you waste energy and so on, as always. Because of the second principle of the thermodynamics, you always lose. But in another sense, you want to use 100% of your material, whatever the energy consumption, and limiting as possible, if possible, the energy consumption. You put it into bitumen with some other aggregate. Because the problem with asphalt, the advantage of asphalt is that it costs little. The problem with asphalt is the deformation is uncontrollable. The so-called freeze-thaw, you remember the freeze-thaw cycles. Asphalt has freeze-thaw cycles, which are very, since it is also black, it absorbs heat very easily. And what happens in practical terms is that it can go as low as -10 or -20 in some cases degrees, and it can go up to 70 or 80 degrees if the temperature, the outside temperature is 35 or 40. And that means also that these freeze-thaw cycles produce a considerable deformation, and that deformation creates cracks. because in reality it is sort of elastic in principle. It's made from smooth stones, etc. So it is an elasticity which translates in the end in the formation of cracks. It is not tough by any means. So if we are able to make it more elastic, but with for longer deformations by adding, for example, tires at end of use, rubber tire at end of use, of course made into small chips, etc. We can use lignin as well, and we can reduce damage, and it reduces also the formation of grooves, because asphalt, what is typical with asphalt, especially when the soil starts sliding, you have the formation of these grooves, which is rotting, and this is a problem for asphalt duration of asphalt. And please always remember that the first sustainability is the duration of the material, so the lower generation of waste. Lignin can be used also in other ways, more research intensive, I would say. You can have this kind of lignin molasses when you manufacture paper. You have this kind of molasses which are added with these alcohols that constitute lignin are added with sugary substances, basically polysaccharides, and which are not as treatable as to make paper, but on the other side, we need to remove them. We need to remove them because consider that paper is made for a longer period. It was made from even if you don't come back to papyrus, but or from to sheep skins like parchment. But if you come to more modern times, well, paper is it's an interesting subject. I hope to be able to spend out an hour or so talking about everything. But paper was made of cotton waste. In fact, the rubbed down cotton waste was collected. They were called the cenciaioli, which were collecting this kind of cotton or hemp or flax and making into paper. Them into paper. I feel like cotton is full of cellulose. Then at the end of the 19th century, paper was made from poplar. Poplar, because it was growing fast, lasted just a few years, but it was able to fill with water. Although poplar has not a particular amount of cellulose. Probably cellulose is around 30–40%. So the rest is lignin or hemicellulose. And as a rule of thumb, you can say that if you have an arboric, so a tree, if you have more than 50% lignin. Otherwise, you have a plant, a vegetable plant, which is not considered. If you have less than 50% lignin or cellulose. Okay, so you can have this kind of lignin, or you can have from the production of sugar as well. You can have from the sugar cane, you can have this kind of molasses. Anyway, you have this lignin more or less CUT in a sense, which was always treated with to get away from polysaccharides. So, and you can make some polyurethanes, some biodegradable polyurethanes. I was talking about polyurethanes, and polyurethane is a big, has been used a lot. It's a plastic which has been used a lot, and now you can make it biodegradable, sort of slowly biodegradable, but anyway, biodegradable. So you can substitute the polyol which are used into to make so the polyvalent alcohols basically. You can make them into this kind of byproducts from paper, from sugar, and you can integrate into this production. I don't go into details into this production, but basically you have this kind of waste and you can produce these foams. So this polyurethane foam, which you know all too well, because of the filling of most sofas, chairs, etc. And therefore you can make it them in a more sustainable way. That's a positive. Another possibility, of course, is to produce other chemicals. For example, polyethylene glycol. You can produce them from lignin, from waste of lignin, and introduce into the preparation of the production of polyurethane. Polyurethane foams are an example. Another thing you can do, and there has been, you may remember that I was saying that we could produce, for example, something which can be sort of thermoplastic. Well, not wood is thermosetting, which creates a number of problems. Wood cannot be molded. Wood cannot be sort of translucent. Transparent will be too much, but even translucent is not possible for wood because there is lignin. But you can depolymerize lignin and eliminating also sulfur and making this kind of product, which I'm going to discuss later on, which is the arboform, which is called in an aggressive marketing way liquid. Well, it's not liquid; it's moldable, sort of moldable into pieces of a definite shape, and it's sort of translucent as well. Then another material which comes from lignin, which is byproduct, is bagasse, which has been used even to produce paper, because it's rich in cellulose. It is a byproduct of production of sugar, and it is thermoformed in biodegradable products like this dish, but there are a number of uses of this, and which are also of large interest, because I can tell you that one of the other possibilities which has been looked at a lot is the fact that polymer based composite, polymer matrix composite, for example, fiberglass. In fiberglass, you can think of the possibility of replacing glass fibers with a natural fiber. Also with kind of bagasse fiber, for example. Of course, you lose strength, well, but it is more sustainable, and anyway, anyway, at the end of life, you don't have the problems you have with fiberglass. In recycling, it's very difficult to recycle fiberglass, not because of the fiber, because glass, of course, it's silica, but because of the resin it's put together, which in most cases is a thermosetting resin. Instead, if you put this kind of material, well, you reduce the impact. You reduce the impact. You are not going to recycle it, but anyway, you might not have some problems like silicosis. If you could, if something is thermoset, you can also chop everything, grind everything into powder and put it in something else, which is possible if the resin is not toxic, it doesn't develop some toxic organic compounds in particular. And if the ceramic doesn't create problems, for example, health problem, for example, breathing problem, as it is the case for glass powder or for asbestos powder, which is much worse. So there are a lot of considerations into trying to introduce these materials back again into the productive system of natural materials. So this is the Arboform, and let's have a look what they are trying to do. Of course, it's a kind of living material. So in practical terms, you see this panel and they burn it. You burn it, and in the end, they wanted to demonstrate how much they were in the wood, and they wanted also to demonstrate that they were self-extinguishing. Because the problem with cellulose-based materials is that we started with materials which were self-combustible, not self-extinguishing. Nitrocellulose, which was one of the first plastics that was developed in the 19th century, was self-combusting. And with wood, you may remember that what was saying and a bit talking about this time that we don't want any more fires, so we are going to replace wood with, which has other problems, of course. But anyway, this material is also self-extinguishing Arboform. In fact, they have done tests, and you can see here that it is likely to be, because in reality you can see that the material is very even. So you obviously you have some larger plates, you have some smaller plates, but the degradation is gradual. Probably the material gets fire because the degradation might be too fast, and or because it contains some substances like some elements like sulfur, which are going to trigger the combustion. And here the sulfur is removed, so it doesn't take fire, and you can mold it into granules. This is the initial, the beginning of the story for plastics. You have granules. Then granules you are able to injection mold them and make into products, etc. They do some, you may remember last time we were talking about micro indentation. Here you, well, nano indentation of diatoms. Here the indenter is much larger, so basically you push with this tip on your material and you see what happens. You see this kind of stress strain. And the problem with natural materials is always the same, that we have quite large variations. Here we have 3 specimens, and you have large variation between the 3 specimens. And we need to be aware of the fact that with natural materials, what happens. And this is a limitation because we are accustomed to steel, and with steel we have little variation between. So I would also say that with natural materials, to perform tests just on 3 samples has little meaning. Whilst on steel, 3 samples would be fine. 3 samples, they have about the same properties, so you are confirmed. You test 3 samples just to be sure that the other 2 repeat what you have found on the first one, but it is usually the case with very little differences. In these materials, it's never the case. In ceramic materials, it's even worse. You need to test 30 to 50 samples in order to have an idea the range of load and the range of strain you are going to get, and of course, the range of stiffness as a consequence. So wood depends on the properties of wood, depends on the fibers, the length of the fibers, and here you see the typical situation for wood bending test. Bending test, you have this kind of typical stress strain curve, and you have an elastic modulus, which is called the usual limit of proportionality. You have an elastic zone, a plastic zone, which is usually quite short, and then they tend to degrade. You can see that there is not a real necking into wood because what happens is quite complex and it's determined by the fibers, and it's also quite difficult to measure because depending on the fibers, for example, if you compress them, well, you can have a large force at one point and a small force at the other point. When the curve is larger, you can have a smaller force, even if you apply always the same force. So that's why compressing wood is determined a lot by the effect of compression wood is determined a lot the orientation of the fibers and the length of the fibers. And also the amount of fibers you have into the matrix. If you think of solid wood, you have this kind of fibers which are more made into lignin, whilst what is in between is more made of cellulose. I wouldn't say that it's all lignin along the fibers and it's not all cellulose between the fibers, but it's not that far from the reality. So this is what I was saying about the measurements that even Stradivari started to do this kind of measurements without having the velocity of sound. But there is a way of cutting the wood or firing bows, and you can see some different meters per second, which depend also on the development rings, because fibers, what we call fibers in reality, are development rings of the tree. And they have different dimensions, and they can tell us about the age of the tree. There is also a science based on that, the endocrinology, which is able to tell you what has been the history of, and in some cases you are able to tell that as some very ancient phenomena has been well, the growth of rings in a tree is able to tell you that a storm has occurred, for example, 100 years ago, which has been studied, reconnected to some historical information. This is also something very interesting. And in terms of materials, you have this kind of cycle which starts from logs, bolts, etc., and then you have the wood strands, which you know to the OSB, and you can have a number of processes. Well, it is not a real cycle, but you have a number of possibilities of obtaining wood. You can manufacture panels, you can make a wood composite with some by pressure or with some glues. And you can also bend them in a permanent way, for example, by the effect of vapor. And I'm going to possibly show you something next time, a little bit more about wood, but not just not much because time is short, but then introducing other natural fibers and passing to polymers, to synthetic polymers. And these are the ways that wood can be, some of the ways that wood can bend into permanent ways by just the effect of the paper, for example, as I was saying. There are some processes which has been important into wood technology. The development of especially furniture of pieces with curved surfaces. So the so-called tonnet chair, which you see around still. They also use it in Vienna in 50. Well, it was. There is the history that Tonnet, or one of his fellows, has thrown that Tonnet chair from the Eiffel Tower, which was just inaugurated, and from the first terrace, so it was around 70 meters, and it got impacted. Apart from the history that it's probably true because they are very resistant to Tonnet chairs, it was the first development of curving, the curvature of wood with paper, which in terms of material science and technology, it is one of the biggest developments. Because wood wasn't able to be curved in a repeatable way, and reliable way, especially doing main pieces all curved in the same way. So we are almost at the end of our lecture, and I give you some orientative values about what we get in the end in real wood. And you can see here some trees and some trees, and we have actual model structure and strength. We are so far from steel. We are probably in order of magnitude below. Flexural modulus as well. In steel, we would have measured tensile strength in most cases. Always remember that what we measure, the strength and stiffness we measure, depends on the force we suppose to apply on the structure. Then, which is a dry density. The problem with wood, the problem and the advantage of wood in some cases is that water enters. Because, well, lignin is hydrophobic, more or less. Cellulose, also cellulose, hemicellulose are hydrophilic. But as a matter of fact, you have some water penetration. In fact, you have to protect, especially if you use for shipbuilding, for example. There are varnishes, dyes, treatments, etc. Having said that, you consider a dry density, so density without water once the wood is dry. And you can see that it's well below, in most cases, it's well below the real density of water. I conclude with this graph up left. You may remember one of the previous lectures when I introduced also natural materials. I was talking a bit about feathers. about chicken feathers, or duck feathers, which have this kind of honeycomb structure and they allow densification. In practice, well, here is for compression. What happens if we compress? If we compress wood and we have cells inside, wood comprises cells. You have most cells if you have cellulose, and with lignin you have basically a dead tissue, and the cells tend to be stiffness and less compressible. But in reality, what happens? You have this kind of, you have an elastic loading, then you have a buckling. Buckling means that it's inflected some ways. And then you have a densification. Densification means that stress goes up and basically with not much strain. The difficulty with that is to recover that. Of course, you don't come back on the same way, but you come back on the leaving some compressive strain. Above, especially above a certain limit. And in fact, after compression, you can see if there are no other problems with expulsion of parts of the material and with tearing of part of the material, you come back with some compressive strain. You won't come back to zero, and in fact, sometimes you have a kind of hysteresis cycle. Hysteresis cycle means that you have an area between the going curve and the returning curve, which is an energy which you have spare, which you have okay, as always, as it is the idea of this course, please concentrate on the real research questions. What is most important in this course, apart from the characteristics, you may easily remember, you may easily understand that you will, even if you remember factual models of OD, you will forget it tomorrow. But this is not the question. The question is to concentrating on the main research questions that are made in material science. And some of these are made also into so it is important, for example, increase the densification. Treat wood in order to increase, or treat honeycomb in order to increase densification means something. And that's how material science research works. It works like any other kind of research. It works on specific problems which are addressed over time, and new materials are developed. Well, there is a lot of marketing also in materials. That's a big problem for a person who wants to buy materials. But if a material is developed in the right way, it answers a question. It answers a question. For example, I might have a material doesn't inflect like a sea. Compresses it is compressed evenly, uniformly. That's, for example, a research question. Or making a moldable wood, it's a research question. One from I have no relation, of course, with armor, with that marrow, that armor, but making wood moldable without putting a resin, that's a question. That's an important technological question, and that's something to which you can give 50 different answers, because if you have a fair, not a media-like conception of science, there is not just one right answer. There is a problem, and there might be 50 different answers. If you have a headache, there might be 50 different drugs that allow you to, or not just drugs, or even drinks. Someone is helped by drinking coffee. Yes, and I think someone is. This is not science fault. The question is that problem can have a number of different solutions depending on the situation, on the individual, and on the availability. As I mean, to come back to Ulysses, Ulysses wanted to make a bed for him and he had olive tree and he was making a wood with that wood bed. Of course, you can make a bed with hundreds of different woods, metals, even plastics in some cases, some kinds of plastics or composites, but the bed wouldn't have the same geometry, the same thickness, and wouldn't be designed in the same way. That means that we have 50 different answers, but every answer needs to be pursued up to the end. So you need to be coherent on that. You decide that you want to make furniture, piece of furniture in an oak tree wood, then you have to be coherent with the personality of the material. It's got its own personality, and which is given by flexural strength, flexural models, and all the characteristics, degradation, temperature degradation, etc., workability, etc., and also by some other characteristics which are not that easy to be predicted. That's why material science is there. Okay, so see you on Friday at 11. We complete that short passage over wood and we carry on with natural materials and we try to produce also later on synthetic polymers and composites and let's see where we can get with